sure you invest in something that's more rigorous or something that doesn't take so much fuss and it doesn't move as long as you fix it.
True. Yeah, it's a good start. There might be like a tripod that would be better that maybe you could even put here so people can see the slides but can also see your face.
Yeah, that might be skewed or something.
Well, and I don't want it in
get
front of
too
anybody.
high. Right.
But yeah, that's definitely doable, for sure. Sam takes a lot of pictures of her pieces. She might have some.
Let's make sure we get the upload stuff on top of
Yeah.
that. We'll keep improving. Alrighty, happy Thursday afternoon. This is a momentous occasion because we're starting the next geological lesson. So we've concluded with one, and that's fine. I think we're getting most of the bugs worked out, not all of them. Before I get going, anybody have any questions? And if I were to wrap it up a little bit, climate sensitivity, or at least on the last exercises, you saw we got some information on the first day. The second day, we thought a little bit about analysis, and then we put it to use. And they were a little bit of working definitions for the third day. We've done the definition, so number one was to apply it in some way. Question number one was basically to apply it. How do we actually use, or what's the significance of climate sensitivity, not the definition of it. Challenge some of us had on 2 and 3, and I apologize for having the positive and negative arrow colors wrong. I thought I'd be fancy by putting them in there, and I got them in there wrong. So that didn't help, but, and some of you adapted and said, I'm using this one, the other one. But the challenge for a few of us was closing the loop. We always start off with an example because we talk about linear things. So I started off the sea ice example with the ice. And you change the ice, and then this changes, then that changes, and that changes. It comes back and changes the ice. That's the operational definition of the closed loop. You could start that anywhere. I don't think I made that necessarily clear. I could have started with warming the water temperature, and that would change the ice, and that would change the albedo, and around it would go. So a loop is exactly that. There's no starting point, no stopping point. The system is interacting all the time. That's a real take-home message. And those systems where they loop are these feedbacks, and they're a big unknown. They are both a known unknown and an unknown in the climate system. We're still discovering some of them. So anyway, let's be sure that we're comfortable with feedback loops, be they positive or negative, accelerate versus regulate. The math is not bad, comparison between the estimate and observed. I don't know what that means. I don't remember what the question 4 was not about that, was it? No. Question 4 was about, what was it about?
It was nonlinear systems. Nonlinear systems, I think.
Okay, so that's what I've got to check in there. If you think about algebra, you've drawn equations that are linear. And that means a straight line, and that means nothing fancy with it. It's just one simple variable. It's a little bit fuzzy, but linear systems are those that respond in a predictable way. The equations that dictate that thing do not have to be linear in nature. There's quite a few things like the stock market, like exponential growth, which would still be a linear system because it's always behaving in the same way. There's not necessarily any discontinuities to it, or bifurcations or steps. And we'll talk about, I'll go back to those. So that made it, so there was a little confusion about that. And I think what we wanted to get across is that nonlinear systems are ones that are non-predictable. Linear system is always predictable because you can do whatever math you want to, be it equations or whatnot. Things like the fluids on the planet are not predictable. Neither the atmosphere nor the ocean, and that's my same main selling point back to the early days. And we would call it nonlinear, we'd call it chaotic, we would call it would have bifurcation points. It could get to a certain point, you can go one of two directions. the way I like to think of it is for us purposes, at least this class purposes, is if the system would be going along and will have variations, it'll go up and down like a yo-yo, and then all of a sudden it takes a step function. So several of you see the word step in my evaluations here. That's because it didn't behave in any simple fashion. It's not straight fashion, it's predictable it had. We can't understand that one of those steps is gonna happen until it happens. In the geologic record, as we've been trying to sort out those steps, it's taken us a long time to actually get to the point where we understood that such steps existed because we couldn't measure them so tightly. I mean, these are the kinds of things where you know, you average it out, it doesn't look very step-like, it's kind of blah, blah, blah. But as you get tighter and tighter control, it looks more like a step. That's a geologic issue. All right. The last one, the thought question, if you have a property called climate sensitive, you want to adapt it, you're an urban planner for wherever, is it a useful thing? Sure, it's useful as a guideline. The question also, though, gets you down to what are you going to do with that information? How are you going to utilize it? A lot of you had some good answers about way you would design for the extreme cases or for the non-extreme cases. And the climate sensitivity, in this case, I'm not challenging the concept of climate sensitivity. I'm asking you to take that and say, well, it's a guideline. And so how do you predict the future if it's not going to be, if it might be predictable, but it's going to change? And so, you know, I think we got around to some discussion about how to do that. What I'm also going to try to convince you as the course goes on, what if it's not predictable? What if the change is not predictable? How do you plan for that? So you'll see the same question. It might not be about a planner for your town. You'll see the same fundamental question. How do you want to prepare for things that you can't predict? Now, sneak up on us, not necessarily in this unit, but further ones, a couple more down the road. Anything I could answer that I haven't explained or misexplained or confused you by right now? Climate sensitivity we won't talk about so much again. The concept of nonlinear systems a lot. All right, closing the book then. We're going to go to hydrology. Or turning the page, I guess. We're going to talk about hydrology. The title of the lecture is, which way is it? Deluges and droughts, or droughts and deluges, I don't imagine, but they're sort of the opposite sides of the same thing. Too much water or not enough water. Well, hydrology is the science that's concerned with the properties of water, and in particular its movement in relation to the land as a working definition. We're really worried about rainfall, for example. I'm going to focus on rainfall for a while. If we think about it though, all of the water that's on land at some point came out of the atmosphere. That's not necessarily true if you talk about water that's down deep in the subsurface, but I'm talking hundreds of feet or thousands of feet down in the subsurface, and that water has a slightly more complex origin, which that doesn't matter for the climate system. So we're not going to delve into that. So we want to talk about water. We want to talk about its properties, and particularly its physical properties right now. I mean, we all know it's an essential ingredient to sustain us. But if I want to talk about its movement in relationship to land, I'm actually going to talk about precipitation, rainfall, or snowfall. For now, they're one and the same. The purpose of this lecture today is to convince you that they're not static in time. I'm going to stat up a little bit about global precipitation patterns, and then I'm going to go to two geologic examples that basically suggest that they're unstable, or they can change over time. Not necessarily unstable, they can't change over time. And we'll call them a drought or a deluge, flood or not. To get to that point, let's talk about the modern precipitation patterns. So the pretty colors here, this is a globe. The whole globe, and we use different projections, and so low precipitation, high precipitation. It's not a surprise, but we haven't talked about it. Where's most of the energy on the planet? It's at the equator, because that's where it gets the most sunshine. If you have a lot of sunshine shining on a body of water, you evaporate it. If you've got a lot of moisture in the air, it rains. So there's a fairly, at least in the Western Hemisphere, there's a fairly pronounced distribution of where the water is, where the water's concentrated. Here's the warmth of the jet stream, the Gulf Stream. The area over in Indonesia is a little more complex because of the ocean circulation patterns, but there's warmth all over the place. And there's spires of warmth going, of precipitation going this way. All right, so that pattern is fine. The Amazon rainforest is fine. The Congo rainforest is fine. The dry Sierra is fine, low precipitations. The Mongolian plateau is dry because it's high. They don't show patterns in the poles, but those are basically fairly dry places also. It's too cold for the precipitation because of the temperature effect, basically. So those patterns are, this would be an average pattern, I think. Grand average climate. So it's a yearly, and these are millimeters per year. So this little spot gets 6 meters of precipitation, which is higher than this room. Cincinnati, we're gonna get something in the, that much precipitation a year. And so that's the light blue-ish. Okay. To convince you that those patterns are averages, here's my favorite friend thing this morning that has the actual precipitation over a 3-hour window of the atmosphere today. And so you see one striking thing that comes out is there's a lot of precipitation right on the high precipitation. No surprise that it's there today. What might be a surprise a little bit is where some places that might normally be kind of dry are wet. Well, those are storms, those are events. These are the hurricanes that are not the one running into Georgia, and in fact, it's not showing up, but well, it's precipitation up in here. There's another storm out in the Pacific, the Atlantic. So these are where there's moisture, and it's, again, this fluid flow. If I do this in 6 hours, this swirly thing will be over here someplace. The areas are pounding against, that are getting precipitation. There's a lot of precipitation in the atmosphere, and it runs into the mountains of the Andes. Mountains have a tendency to wring the moisture out of the air for reasons, something called the orographic effect. Here's that wet spot. It's not particularly wet these 3 hours, but on the average it must be. Here's the dry spot, the Sahara. There's not necessarily any storms in the whatever, but these waves just go on and on and on and on and on and on. So they will go have these patterns where the average you'll see that, but the instantaneous is a little more complex. Okay, that's fine. Examples of droughts are easy to find. These maybe, we've talked a lot about it. There's been a lot in the press for the last couple of years about the California droughts. And then California had a record snowfall, so that makes it confusing. You can worry about droughts, they're all over the place. One of the things that happens is very pronouncedly when the West was running out of water in the last couple of years is it lowered the water levels of the lakes. And so there are places actually in Europe that likewise are unearthing cities that were submerged at some point. So the droughts are, it's a water issue. If you don't have water, life is challenging. Deluge is a little more subtle. We think of them in terms of storms or catastrophic events like hurricanes or enough precipitation to cause floods. Floods are something we would think about instantaneously. That the Ohio River floods quite a bit because we get a lot of rain and snowfall, and then that wave of higher water walks through. That's not necessarily a deluge, but it's something shorter term. I'm trying to talk today about things that are longer term. In other words, you're more susceptible to a whole bunch of floods, not a flood or two. A flood or two goes through in a few days, most of them. A deluge would be 1,000 years kind of thing. The example I'm gonna talk about is 1,000 years kind of what time. There's something else in here. Okay, this is a Google Earth picture of part of North Dakota. You see a series of lakes here. You're actually gonna get an example from this lake here, Stump Lake. And it kind of is a funky system because these lakes right now presently don't drain anywhere. Water level in this system is bounced up and down, and you'll see some examples of Devil's Lake and something called Stump Lake. And they sometimes are connected and sometimes they aren't connected. And this one's gone up quite a bit in the last 100 years, and I'm going to show you an example from here where now you could actually drive a boat theoretically between these. You couldn't do that so long ago. So there's a resurgence in water levels in the Dakotas, which you kind of think of as dry. And I just point this out to set the term for the example you're going to see. The example is Stump Lake. This one. Okay? We happened to be at Stump Lake about 1.5 years ago. We were looking for something else, but part of the thing that we do is we have a sensor in a boat that gives us what's going on underneath the boat, so we just kind of pay attention to that. And this is the track of the boat, and here's a representation of the boat, and it's kind of looking sideways. And I see the bottom of the lake, and I see water depths 5, 10, 15 meters or whatever. But the funny thing that I see in this is all of this business. See all these things that look like branches. And some of these branches sort of go up above the water level, some of them don't go above the water level. Well, it turns out they are look like branches because they are branches. And so if I have a little bit different view of Stump Lake, looking at the land, here's a series of trees that are happily growing, here's a series of dead trees. They have a white chemistry precipitate on them. That's fine, because this area has a lot of evaporation, and so some of the minerals get left behind. But these are all dead trees, hence the stump names. Now, it turns out, I'm a long ways from those stumps, so I send my handy-dandy little rover here to go down and check things out. And so I'm gonna play a movie of I think I'm gonna play a movie, maybe not. Yeah, okay, so I sent the rover down to grab a branch and try to break it off, and it wasn't clever enough to break it off, or I wasn't clever enough to operate it. These are little shrimp that were greatly inconvenienced by me down there trying to break the stick off. The real point is, why am I breaking sticks off a tree that's underwater? And why are the shrimp not happy? Like, see what the shrimp are not happy. I can see. So, anyway, that's sort of the movie. The PDF for the lecture is not too impressive, but I guess we don't necessarily see. There's nothing. Well, I mean, there's the whole tree, right? Or not the whole tree, but at least the branch of the tree. So and there's the piece of the tree that ate another tree. So I'm figuratively trying to get my thing lost in this forest, and I wasn't clever enough to grab that one piece of wood. If I look again at my imaging and I look where the trees really are, turns out there they are, 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 and they stop. And so they stop someplace 14 meters, 40-ish feet below the surface. So an interpretation is this is an old lake level. The trees were growing up here beside the lake, and then the water is subsequently risen. That's a decent geologic interpretation, but you don't have to believe me, because we can go over to Devil's Lake where they've been measuring the water levels for more than 100 years now, so 1860 to 2010, and I'll explain what's going to happen here. And what they see is the lake levels started going, here's where they started measuring them in detail. These are less frequently measured, and it drops down. And if you actually do the feet to conversion, it's about 14 meters. So isn't that convenient? But for some reason, over the last, since 1940, so over the last 70 years or whatnot, the water levels have been going up. Now, one of the reasons that they don't go up much is because that's when the level in that place got high enough that it ran over to the next lake over. And they'll go up again and run over to the next lake. But this is when the passage to Stump Lake worked. So guess what? Stump Lake was 14 meters below because we could tell the trees. This got over and flooded it, and that brought it up to the modern level of Devil's Lake, so it's a continuous lake now. This is driving the planners there kind of bonkers, because you drive around on that terrain and all these roads end in the water. They laid out a bunch of roads, but the water levels have gone up enough to drown them out. And when we were on this trip, we saw a bunch of farms on islands. And the silos that were half underwater, not well, third underwater. So the water conditions in the Dakotas is changing from a drier to a wetter condition today. Great. I want to look deeper into the geological past to a deluge or another wet period. And again, it's 1,000 sort of years long. And where we're going to go is the Sahara, which today is dry. And we're going to show you evidence that there are used to be a bunch of lakes there. And lakes, by the way, can change land use patterns. Since people need water to do their thing, if you don't have water, there's not so many people. If you have water, there's people that'll do their thing. This particular example is going to happen about 8,000 or 9,000 years ago. That's in the that's after the Ice Age, so we're not talking about the Ice Age problems. We're talking about something that's in the what we call the Holocene, and it's a period of time, well, basically the last 10, 11,000 years when the conditions are sort of normal. This has been called the African humid period, and the study I'm going to rely heavily on is talks about the it's more recent, but one of the startling images that came out when they first put a bunch of satellites in orbit around the Earth was they saw all these dead river basins in the middle of the Sahara. And at that point, nobody could figure out, well, why are the rivers in the middle of the Sahara? Well, I'm not sure we understand why there are rivers there. I'm saying that documented better than it is. So here's the dry pattern. Here's Africa. Here's the wet spot coming across. Here's the dry spot of that. The Mediterranean is not really particularly, all of Europe is up in here. That's not particularly wet, but that's fine. So this is dry. And the manifestation of it today is this contrast between the vegetated central part of Africa and the northern part of Africa, which is basically deserts. A few oases here or there. The center figure, however, is this same area, and it's showing a bunch of lakes and features that require water to form and the pathways of a variety of rivers that existed that don't exist today. You can dig up the evidence of them. And so this is in a paper published about 10 years ago, 12 years ago. So putting this all together was kind of, oh, that's interesting. Why is something that's fundamentally dry today full of lakes? It probably is the same reason that North Dakota was dry and was wet, but on a different time scale, in my opinion. The land use that's associated with this, and the series of archaeologists looked at this, and so I don't know what you want to call the various peoples or types of peoples or groups of peoples or tribes or whatever, but the people that were occupying the Sahara Desert 8,000 years ago go by different names, and they have different distributions, and this one lived here, this one lived that part of the area. These people had a little bit wider distribution, but the real point take-home message is they were hanging around the lakes. Shocking. They had water, they could fish. I don't know if they did agriculture or not. I'm not familiar with that. But there you have it, in the Sahara. If you look at some of without getting in too deep into this graph, this is time. This is the end, this is the maximum of the last ice age just 1,000 years ago. We're out here today. So this is old time, young time. This is 10,000 years ago. These little squiggles are different proxies, different chemical things that you use to try to get a handle on what's going on in precipitation at a particular point. This is from a particular lake, and then there's a core in the ocean. And they're kind of intermixed. But what the authors of this paper concluded is drier times, wetter times, drier times. And they talk about 2 wet periods. We can quibble about whether this one's as important as this one, but there's wet, 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 wet. You don't need to go, you'll have to trust me on going deeply into what all these squiggles mean, but they all show the same pattern, and that's the key. And it persisted for some period of time, a few thousand years. That's not to say, and the lakes were, I don't know how long the lakes are, I don't think we know enough to know. But they did occur right in the middle of this wet period. So we have proxies that indicate it, we have physical presence of it. The Sahara was a wet period, it's now called the African humid period. Flip the coin. We want to talk about droughts. We want to talk about bigger droughts than the droughts that impact farming. Today, a drought of a couple of years makes a difference on, some farmers' ability to keep growing crops. I'm going to talk about the Great Lakes. And the Great Lakes are once a closed basin. What does that mean? They have no outlet. We have one of the largest freshwater systems on the planet. It sits in our backyard. And sometime in the past, it was a bunch of isolated ponds. Well, they weren't ponds, but we were isolated. There was no water flowing out of them. And to carry it to the human extent, one of the example I'll show you, and there are other examples, what they find is if you go down below the water, I found trees, and I was pretty happy with those, but other people using more sophisticated tools and looking at more systematically have found many archaeological sites. And the particular archaeological site that we're drawing for inspiration for this exercise allowed them to hunt caribou. So they took advantage of a particular geometry of this different level of the lake, and we were able to hunt caribou. Again, this happened at the end of the last ice age. I'll give you the clue back. It's 8,000 years. They're the same. They're not instantaneously the same. For our purposes, they're the same time. Dry in the Sahara, wet here. Okay, we're going to delve into this one quite a bit. I'm going to delve into it because I want to bring up the concept of the hydrological balance. We've talked about the energy balance, and that was about your checkbook, money in, going, money out, energy coming in, going out. The hydrological checkbook is a little more complex. It's got other elements, but it's still going to be algebra, it's still going to be math. And so we're going to estimate how the condition, we're going to think about not only was it wet or dry, but how much wetter or how much drier was it? And then what controlled it? Because like your checkbook balance can go up or down because you change the money going in or take the money going out. You can change it both ways. Well, if we got 4 things that we can control, we have a better chance to control it. So we're going to try to think about how do you get a little deeper into the estimation in the past. Great Lakes today, like I said, is one of the largest freshwater ecosystems on the planet. They're here, Toledo's here, Cleveland's here, we're here. These lakes drain out the St. Lawrence River into the Gulf of St. Lawrence and ultimately the North Atlantic. Something like 3 of the 10 largest lakes in the world are in this system. And then Lake Erie's number 11. But Superior's the 2nd largest lake, Huron's the 4th largest lake, Michigan's the 5th largest lake. I don't know why Ontario isn't higher. But at any rate, it's a lot of water. The second point here is that we have a concept called the drainage basin. And what that means is all of the water, I think I'm going to show you on the next slide. all the water that falls on the land surface in a drainage basin will go there. So any water, raindrop that falls here will ultimately end up in Lake Michigan. Any raindrop that here ultimately ends up in actually the Mississippi River. Raindrops up here go up to the Arctic. So it's a conceptual idea because it gives us a boundary around which we can worry about precipitation patterns. So it's important to know the drainage basin. We're not going to use that per se in our exercise. We're going to talk about the area of the lake, though. All right, so that yellow area is the drainage basin. It eventually drains into these lakes in this case. This ratio, this balance between how much area in the side of the lakes is really skewed for the Great Lakes. That's a really small drainage basin in proportion to the size of the lakes and the amount of water that's in them. And that indicates that there's a pretty healthy precipitation pattern here. Or, the other way to get rid of stuff is to evaporate it. So it indicates this is a pretty healthy evaporation area, one or the other. These things are dictated, the drainage basins are dictated by topography. All right, this is a graph of the Lake Huron, I believe, basically. And the problem that we had for many years is we knew there were former changes in it. We knew it had higher levels, we knew something about those. We knew there were trees growing on the bottom of Lake Superior, on places on the bottom of Lake Superior. Not Superior, Michigan, excuse me. But we didn't know how to sort that all out, because in this particular case, when the glaciers left the area, they had pushed it down and it came back up. And so before we could actually get a sense of what the lake levels look like, they had to tease out this rebound problem. We're not going to go into that, but that's why this curve is this gray curve is here. This is the elevation of the outlet. And so this is time, 14,000 years ago, the end of the Ice Age, 6,000 years ago. And we're seeing a high level, it's got a name, and then another high level, and the blurb, and then it back to the blurb, and then the low. And again, we couldn't sort this out until we get the fact that we had to take this part of it off. And I don't care about all the rest of this stuff, but I do care about the low, because that's what we're interested in here today. So this is the elevation of these things relative to what would have been the outlet. The outlet migrated over time, so the height of the lakes actually migrated over time in some rain frame. So they were bigger and smaller. If we had a paleogeographic reconstruction, if we tried to look at the topography of the basin, current basin, the area in yellow in the last couple of slides, here it is, today, we color scheme these so the reds and the greens and the oranges and things are how high above the present day lake. The blues and whatnot are how deep the lake is. Lake Erie's not very blue, it's not very deep. Huron, I'm missing Superior, but Huron is pretty deep, Georgian Bay, Ontario. And so here's this topography. We're going to zoom in on Lake Huron here for a minute. We've missed the Michigan and Superior. The white line is the present shoreline. So in other words, if this was a satellite image, we would see this as water. And we would see the topography, whatever. The black lines are where it was at some point, at that low point. And what else can I tell you about this diagram, gentleman in the red shirt? Or anything else we've talked about? We're talking about the topography, talking about the fact the lake is a hole in the ground, so I'm not. The hole in the ground, though the size of the lake depends not on necessarily on the hole in the ground, but also where the water is. And what we're doing here is we're taking this is the modern lake, and this is the lake we're dealing with. Trying to make sense or no?
Yeah.
No question?
No.
Anybody else want a question? they're free, you know. They even get answered occasionally. Zooming in on Huron again, excuse me. These are the colors. Well, one of the things we see about this is that there's a lot of, it's not simply a hole, it's a whole complex hole. And this is an arch of bedrock that breaks off Lake Huron from the Georgian Bay. And this is a great Canadian tourist area because it's all islands and bays and things. So there's an arch of bedrock that controls that high. Well, if you look carefully, there's another arch of bedrock, there's two of them actually, connecting Michigan and Ontario that are in the lake. And so what we're gonna do is we're gonna grow a lake level enough to make this arch, like this one, standing above the then water level. And then you've got a pathway, super highway, if you will, for caribou to go back. So this is the construction that actually, it's not modified by the lake at all today, but it controlled the lake, and because the water levels go down, it provided this unique opportunity. We're gonna zoom in on just this area. In fact, we're gonna zoom in on just a very small part of the lake right now. Zoomed in again, here's all the whole lake. Here's that archway, or one end of the archway. This is Michigan, Ontario's way over there someplace. This is what would be modern land today, the modern shoreline. This was the shoreline at that time. And this is the area that's converted between underwater versus trees. And if the water, at some point when that water came back out, just like Devil's Lake, all these trees got drowned. But it was thousands of years ago, so they're not there anymore. And we're gonna zoom into one spot on this, and he's got a name for it, and it's an archaeological name. We're gonna zoom into it again. So here's the edge of the water. Here's the water edge on the other side. This is only about 1.5 kilometers apart. That's the other. It's a little bit wider than the campus. And what people discovered is there's a whole series of boulders lined up here and there. And then there's little escarpments here. And so they got wondering about it. And one take-home point is this place is 37 meters below the present water line. We're gonna use 37 meters as part of our control center. But taking a look at what's there, here's all those rocks. They're interpreted to be water, some rubbly surface, something that was wet surface, and these rocks, and these lines, which are rock walls where presumably the hunters could have concealed themselves, what not. But the caribou like to migrate, and they're fine, they migrate over the whole terrain. But then when they're on this isthmus, their migration paths are constrained. So the humans at that time made them more constrained. They forced them to go in and out of these little funnels, and then they laid for them here and were able to harvest them. Because why not? So this is the archaeology of the thing. This is the land use adapted to conditions at that time. And one more thing to emphasize that it is an archaeological site. Of course, they found all kinds of archaeological tools, hunting tools, that were abandoned because they had to eventually give this set up because it drowned again. All right, little nuance to this. Caribou like to migrate each year, or each half of the year, one way and the other. So it turns out that during the autumn, they came from northern Michigan down to Ontario to be a little bit warmer, and then in the summertime they migrate up. And caribou do that today all the time. They migrate great distances to go to their birthing grounds in the summertime, and winter times to be a little less hazard. So these folks had two meal tickets twice a year. Pretty cool. All right. And you're gonna have to accept me at face value. Here's time of the Holocene, the last 10, 12, 14,000 years. We have some indicators of two properties here. but our target area is this business about 800 years ago. I don't care about the exact number, but 8,000, same as the Sahara. What we see here is that there's reconstructions of moisture, not rainfall. Rainfall itself is actually hard to get in the past, but we can do something with moisture. We can also do temperature, that's pretty good. And so these two have a similar patterns. A cold, dry period coming out of the Ice Age, the modern warmth, a moist, warm period, a dry period, warmness, dry, but then just sort of at the transition from here to here, this lake level drop. Transitions are important sometimes. But we see that those conditions were quite different than today's values. All right, so I'm going to set up the problem. From here on, it's a balancing checkbook with 4 different accounts in it, if you will, 2 in, 2 out. Migration, we're going to call it 37 meters. That implies there has to be a different hydrological balance. The lake today bounces around, but on orders of sort of the height of this room, or less. So there are hydrological balances on smaller scales, but 37 meters is the height of this building-ish. And so can we get an estimate of not today's balance, but the past balance? Yes. Math involved, here we go again. We're still worried about the things that will add water versus the things that will take the water away. When today, what takes the water away is the outlets, the big rivers that run out of the lakes. So we can measure those. This lake was below that outlet. So there's less things that could have taken the water away back in that day. All right. We're only going to consider a piece of the Lake Huron Basin, and I'm going to simplify the geometry to make it more palatable. Here's the simplest expression of hydrological balance. And I'm avoiding some of these things, not scare you off, but there's a concept here we need to talk about: flux. Flux is called the sort of a volume per some time. And what that means is, if I want to measure, say, a stream, I want to measure how much water is going through that stream for a given unit of time. The measured unit that we'd like to use is meters cubed, and a meter cubed is yay big, which turns out, if you have to drink it, it's a lot of water. And we can use meters per second. You can use meters per second, minutes, or whatever. I think we ultimately want meters per, well, this one's in meters per day. Doesn't matter, we need to keep on the same point. Generally, in equations about water, the water flux into and out of the system is called Q, the discharge. All right, so in the simplest fashion, here's a lake. It has a river running into it and a river running out of it. So what are the things, in broad senses, that can input flux in some meters cubed per day? Well, rainfall. That's fall. What's the rain that's falling directly on the surface of the lake? Okay. We can talk about whatever's coming in the stream. Different beast. We can talk about stuff that goes underground and gets into the lake. We're going to ignore that one because it's hard to get a handle on. And we can talk about stuff that just runs off from, isn't in the channel of the stream, but nevertheless there's some water that comes in around. So those are the big inputs: precipitation, the inflowing stream, and this one's miserable. And this one's not big enough to worry about for us. So we're going to just go down to these two. A one that can be, so on the output side, which is on the other side of the red card, we have what? Guess what? The stream that goes out. That's one. The water that might go into the ground and go someplace else. And then the third one, evaporation. You get rid of rainfall, water leaves the lake directly by evaporation. by definition, our exercise is an example where this is down to 0. We're ignoring this one. So we're really focusing on this one. Evaporation and transpiration, they call it. That's the transpiration in the basin because that's what the plants kick up into the air. The stream outflow numbers and the groundwater flow. So you see how this, I hope you see how this balances now. Who needs to ask me a question? In and out, the water has to come in and go out. We can partition it different ways that comes into it. We have to have some sort of common denominator, our flux, to make the checkbook balance. We can't talk about pesos and dollars and euro.
So there has to be like, you said there has to be like a common balance. So what would an example of that be?
In theory, you should be able to say that the water balance, the hydrological balance for any lake or any body of water, whatever you want to do, is in, well, first of all, it's in balance. So all of these things have to sum up to 0 if the lake's not changed. Okay. We are looking, since we know that Huron changed shape, we know some changes occurred, but we're going to try to find what was its balance then. We're going to assume that there's no big changes. So we're going to talk about the flux. The math is going to drive you the most nuts in this exercise is getting a bunch of different numbers into the same unit, because otherwise they don't subtract. I'm just getting the same unit, that's all algebra, yeah. And once you get out of that, then it's subtraction. All right, gentlemen back here.
What's transpiration again?
What is transpiration? Plants draw out moisture from the soil, and they, in the part of their photosynthesis, it transpires out of the leaves. So it's sometimes you see it as transfer evaporation, actually. If you want to consider the hydrological balance of the modern day lakes, you have to consider plants because they cover. See, there'll be some rain that will fall on the land surface, but then it'll get turned around and sucked up by a plant and spit back in the atmosphere. So you have to subtract that out. Again, we're going to simplify that. We're just going to go down to evaporation from the lake basin. Not worried about the surrounding areas. Anything else? And there's a couple equations that are hidden in here because it turns out that volume's also involved in this because all of these numbers, if you have all these numbers, you put them together, it works for a certain volume of the lake. If you change the volume, you had to have changed one or more of these things to get the volume change. Here's our model. I've tried to color code it. Water blue, water out, green for whatever reason. Change in volume is something, how much it changed this way, that's in purplish. And blue is water again. So conceptually, water in minus the water out has to be change in volume. If it's in balance, these two numbers add up to the same, the volume doesn't change. Most lakes today can't change volume too much because they can adjust any precipitation changes by just throwing it out the stream that comes in. So that's our simple model. Now, we're going to break the water into two parts. Rainfall that falls directly on the lake, plus any river that happens to flow into it. And for our model, it's going to be one river. And then we have to subtract the evaporation, and again, it's the evaporation of that lake. And we're going to have to say, we're going to subtract evaporation plus whatever river flow out, change in volume. We're going to zero this one out for simplicity. So it's a change in volume. And for this exercise, we know the change in volume. We know the answer. So we're going to take that answer, and then we're going to take the modern values of these, and we're going to see what we have to do to them in order to get that thing changed. And I'll say it again before I'm through. Okay, this says meters cubed per year. Let's double check that we're always using that unit. Because you will find it published, today's exercise is go find a precipitation value. Now, they may not be in meters cubed per year. Probably won't be. It'll probably be millimeters per day or something. A whole bunch of zeros. So this will be a challenge. And what I'll tell you to do is online, you can get calculators that will do that. So do a Google search. I have millimeters per day precipitation. What is that in meters cubed? You'll have millimeters cubed per day. What is that in meters cubed per year? They will give you the right number of zeros. Okay. This, if I'm doing this for real lakes, really depends on the volume of the lake, and the lake doesn't have a simple volume because of these holes. And so if I change this one some, that's a lot more water than changing the same level of the lake down here. For us, we're gonna make it a box, because it's a lot easier to calculate. And so what we're gonna do is our change of volume, we know that number. We're gonna find this number, we're gonna find this number, we're gonna convert it to this. We're gonna call this 0, get rid of one of them. And we're gonna worry about this. We're gonna take the modern day values, and we're gonna get an estimate of how workable the balance is. Now questions. I'm sneaking up on this, it's not complicated, it's math. After you get this done, that's multiplication, nasty, nasty. Okay, oh look, an exercise. Find the values for all of those things. How much is actually going out of Huron today, just to get it that number? So that's gonna be Lake Huron, Lake flow into Huron. A little bit of challenge with this one is because both Michigan and Superior flow into Huron. So you might find one or the other, or you might find them both. So don't overlook that. One of them big enough matters. How much goes out of Lake Huron, that's more for reference, because we're gonna cut it to 0. What are the precipitation, both rain and snow, that falls in the area of Lake Huron, or on it? What are the evaporation rates? That'll be the hardest one to find. It turns out not easy to measure. The surface area today of Lake Huron is gonna be a huge number, and that's easy to get. There's our fluxes again, keep the fluxes straight. Second question for today, or for Tuesday, and it's a thought question. Oops. The two examples that we had from the paleo, 8,000-ish years ago, have one area getting wet and one getting dry. What do you make of that? You're gonna see the question again at a deeper level. Questions? Free time, good time for questions.
For the second question, are we looking to identify a pattern that would relate the two?
Not necessarily. I suspect you've never thought too much about different regions getting wet and dry, so I just want to get you to start thinking, could that mean anything? Could that be coincidence? I mean, I don't believe it. I don't believe in coincidences.
I wouldn't believe so either.
Excuse me?
I wouldn't believe so either.
No. But if we start down that line, then we can explore possible reasons that they might be linked. And that's a different topic, sir.
Do you know any good resources for finding these values?
NOAA has some. There's also a Great Lakes, the Great Lakes hydrological balances are studied fairly intensively. They have different, each lake has its own thingamabob, or the USGS. There's also, because the lakes are, at least Huron and Superior are both in Canada and the US, there are Canadian resources. What you're gonna find though is you got way too much information. We want a simple per year value. They're gonna give you every little change over the last 20 minutes. I mean, figuratively, you can find a place where you can get the water level changes from the last day.
Okay.
That doesn't do us any good. And we're not concerned about the water level changes necessarily. We just want to get to the right number of zeros, first order estimate, how much these things are. And I'm going to ask the question back to why this might be evaporation transpiration. We could go over the Sahara and have the same thing. Was it wetter there because we cut down the evaporation or because we had more rainfall? 99% of us would say, well, it's more rainfall. Evaporation takes it away. You change evaporation, you leave more. Showed you my prejudice already. We need the lady sitting in front of Liz to ask a question.
I would say whenever you said that evaporation finding out going to be harder, does that mean it's going to be harder to research or harder to find like mathematically?
The find mathematically is easier, but it's a harder measure to actually make. So I've seen graphs of tables of evaporation, and they'll say the evaporation around the Great Lake, around the Huron. And so you'll see that there might be a set of different numbers, because the evaporation up in Sault Ste. Marie is not the same as evaporation around Detroit. We don't want to worry too much about that detail. Go where we're at and pick a number in the middle. Okay, so, but evaporation in general is a lot harder to come by. The values for evaporation. And over land they're even worse, but that's a different story. The rainfall is more interest, so the people that do the actual measurements, they post the information, and then the second order sites pick up a lot of information. So that's why it's easy to find those things. Less people care about evaporation, so less secondary sites have picked it up. Okay? Sir,
Do you upload the PowerPoint today?
did I upload the PowerPoint today?
Yes, and they're officially in the modules, and I made sure the assignments are up now too. So everything should
And
be
it's a
good.
big PowerPoint, I think.
It's a chunky one, yeah, so it took a little while, but it's up.
Okay. But still not on my side.
It's not on there,
It's
your
not,
side.
let me make sure that.
Okay,
it's-
Liz is working on that. In the meantime, I'm gonna take another question, okay? Thank you for putting that out.
For the second one, like, are you asking for like an example of like when there was like a drought or a deluge, like?
No, I'm giving you a example of both of them, of two, drought and the deluge, big ones. Bigger than we've really seen in the last 8,000 or 9,000 years. So it's back to the coincidence or not. I mean, you know, geologists are always trying to link cause and effect. And so somebody would study the drought in the Sahara, and they would think around the Sahara, and they would worry about why could the local Sahara change. Fine. We're delving into why Lake Huron could change, and that's fine. I'm asking you to think, you suppose there's any connection to the two? We should find not an explanation that's localized, but something that's more broad. Again, I'm pretty sure nobody's thought about these kinds of problems, but that's part of what we're trying to do, is think about things a little differently. Okay? Question? No? All straightforward?
It looks like on the actual desktop it's up, but on the app it's kind of finicky. Are y'all using the website or are you using the app? Okay. It's up on my end. I just took everything down and put it back up, so if there's a hiccup there, let's see what happens.
Mine just says the module is unpublished.
The module, the whole
Yeah.
module's on
I took it down and I put it back up.
I think it's
Okay.
I see it right now.
How many people are how many people are getting it? Or
Yeah, how many
have
people can
checked
see it?
So they get it, so
You can see it, you can
several,
see it.
how many people are not getting it so far?
Okay.
We've got a couple, okay. So we've gotten better since we've messed with
I think it was just taking a hot minute and getting itself up.
it. What we can do is- Anything else I can tell anybody?
And y'all can see the quiz, right, the homework assignment?
Excuse me? Can you
Sorry.
see your evaluations of the, right, can you see the quiz, the questions? Okay. You're gonna spend most of your time messing around with this. Get the number, go to a conversion website, get the right number. Years ago, I would have forced you to do the math because the math is a good exercise for you. And it would drive you nuts because you get the wrong numbers. Now we can find the right numbers. You're good to go. All right, in that case, let's reconvene on Tuesday and have a safe Memorial Day weekend, please. Yeah, so suggest an engineer how to design a building. This doesn't the energy source, it might be philosophical